lunch. I hope all of you had a nice lunch. So today this will be the kind of hands-on as well as tutorial sessions in which we are going to have demonstration and basics about QuantumATK, basics about the DFT simulations, what are the features QuantumATK have, and some of the hands-on experience. And for this session, I would like to invite for atomistic modeling and simulation of nano devices using Synopsys QuantumATK. Deepak has completed his BTech in Electronics and Communication Engineering from APJ, Abdul Kalam Technological University, Lucknow, Uttar Pradesh. Followed by the work at Legal Design Consultant India Private Limited, Gurgaon, Haryana as a junior design engineer. Moving forward, he worked at Impulse Technology, Gurgaon, Haryana as an application engineer. Followed by he is working in integrated microsystem as a principal engineer. Currently, his mostly working area are EDA tool for Synopsys QuantumATK. Today, he will show presentation and demonstration on nanoscale materials and device simulation by DFT and DFT quantum transport method using QuantumATK software and its application in current and future technology. So, it will give you a lot of opportunity to learn so many things from the Deepak. So, Deepak, thank you for joining us. Thank you for your valuable time. Stay over to you. Thank you.
So thank you for this brief introduction. So very good afternoon to all of you. So firstly, I would like to thank all the advocacy committee who organized this beautiful session, and special thanks to Dr. Zidesh Kumar who given this opportunity to introduce this Synopsys QuantumATK software. So firstly, I will share some brief presentation about the tool and the features that we have in the QuantumATK, and after this brief presentation, we will move to the hands-on. So now how to select introduce this broader Synopsys simulation ecosystem. So at the top we have the Synopsys QuantumATK, and it is an atomic scale modeling software that enables a realistic particle simulation by integrating multiple simulation methods. So this QuantumATK is identified for exploring quantum mechanical properties, electronic structure, and material behavior at the atomic scale. So alongside this QuantumATK, we have the Synopsys Centros ticket on next generation simulator for designing and optimizing these semiconductor devices. So it supports a wide range of materials and physics models, making it suitable for both current and future technology. So Synopsys also offers a complete VLSI package covering digital printing and backend tools as well as full custom solution for the analog and mixed signal to sign off that ensure the seamless integration and high accuracy. So this suite empowers engineers to simulate everything from atom to circuit, and that will enable the faster and more diverse semiconductor innovation. So this holistic approach is what makes Synopsys a leader in the TKD space. So here you can see this is the Synopsys ticket product family that we are representing in India for the technical support. So we have the Synopsys QuantumATK, and this QuantumATK comes with this UI that is called Virtual Nanolab. And in the Virtual Nanolab, we also have the Centros material workbench that will help you to simulate the material at the atomistic level, and then you can further explore in the TCAD simulation. So for the TCAD, we have the process and also the device simulator, and that will help you to simulate semiconductor process steps like the deposition, etching, deposition, oxidation, photolithography, and you can also do the electrical, optical, and thermal property by using the device simulator. So this Centros ticket is also comes with this device, and for integrating all the tool process, structural rating, device simulator, it is known as the Centros workbench. And for visualization of the result in the 1D, 2D, and 3D view, it also comes with the Centros visual. And now for the device level simulation to the TCAD level, spice level simulation, we have the current stick and random spice simulator. So I'm not going into details for this Centros ticket because today we have this session on this Synopsys QuantumATK. So we will focus on this QuantumATK tools. So let me give you some brief idea about this QuantumATK. So this QuantumATK is an integrated platform of the electronics and atomic scale modelings, which is written in Python and C++. So this software is developed by the expert software engineers and scientists to meet the highest requirement of feasibility and efficiency. So this QuantumATK comes with the 4 simulation engine like the density function theory, semi-empirical type bonding model, and also the classical force field and Massillon force field simulation. And for the devices level simulation, we have the non-frame green function method. So in the density function theory, we support two types of basis set for simulating the materials. Like we have the plane wave basis set and we have the linear combination of atomic orbital basis set. Similarly, for the material simulation, we have the semi-peptide bonding models, and in that model, we have the two types of Hamiltonian, Slater cluster and extended Hubbard method. And similarly, this classical force field and Maximum force field simulation will help you to simulate your material at the larger scale. And for the devices, this non-uniform green function method will combine with the density function theory. You can also integrate this CNEGF method with the semi-bezel tie bonding so that you can calculate the transport property of the devices. So this QuantumATK provides the complete solution for the materials and devices modelings with the multiple methods implemented in a single platform. So this QuantumATK is a comprehensive platform for the atomic scale material and device modeling tools. So we offer various effective tools for achieving realistic outcomes, and we also offer a synergistic solution to solve the complex problem. Now if we talk about the effective tool that we have, so if you are a new user, so for the new user we provide a sophisticated graphical user interface, and we also provide the manual and tutorial so that a new user can get started quickly. And if you are an experienced user, so for the experienced user, it comes with the Python scripting that will help you to write a script in the editor, and you can also customize the task as per your need. Now, if we talk about the synergistic solution that we provide, so all the structure editing, builder, job submission settings comes in a single infrastructure that is called virtual nanolab, and you can also do their various multi-physics analysis like the electronics properties, optical, mechanical, thermal, even the electrical property of the devices you can easily simulate. Now, if we talk about the integration of this quantum with ATK with the TCAD, so you can also export the raw data that you get from the QuantumATK software at the atomic scale, and you can utilize this data in the TCAD as a input. Now, if we talk about the realistic physics for the complex materials, so you can deal with the small scale system to large scale system, and you can also calculate the transport property of the devices. Now, if we talk about the bigger application of this QuantumATK software, so the bigger application of this software is for the molecular structure simulation, surface simulation, interface between different geometry and different symmetry, devices simulation, complex materials like hexagonal, tetragonal, traveler, phosphorus materials, polymers, composite materials, and even nanostructures like the nanotubes, nanoribbons, nanowires, you can easily simulate. So it comes with this UI where we have the different kind of builder settings. So molecule is one of them. So you can deal with the organic molecules. You can also deal with the inorganic molecules. And for creating any kind of surface structure, we have to define the Miller indices. Like their scale value we need to define either 100, 101, 111. So whatever the combination we want to create the surface structure, just define the Miller indices, and then the software will automatically create your surface structure. Similarly, you can create the interface between two materials and more than two materials, that is also possible. Now, if we talk about the devices applications that we support in QuantumATK, so we deal with the 1 pro device structure, 2 pro device structure, even 3 pro devices like MOSFET, transistors, you can easily simulate. So these are the bigger applications where you can utilize this QuantumATK software. So with this QuantumATK software, one can model a wide range of applications like the molecules, polymers, 1D and 2D materials, any kind of crystal structure, market devices, you can easily simulate. Tailored UI tools to build and visualize such models, set up the script, manage the local and remote machine, and also the analysis of the result that all comes in a single UI that is called virtual nanolab. So here you can see the virtual nanolab, we have the different kind of builder settings. Now this building tool will help you to create a DRE structure. You can go with the crystals, molecules, even devices. It also comes with the database of the material. So in QuantumATK we have the two options to import the material. So it comes with the database that exists inside the software, and it also provides the online database. So in the online database we support the crystallography open source database, and we also support the material project. So this database will help you to import the material in the building tools, and once the structure is ready, you can go to the calculation setups. So this calculation setup will help you to set up your calculator and also the analysis part, like whatever the analysis, the electron properties, optical, thermal, mechanical, that you want to calculate, that you have to set up in the workflow, and once the workflow is ready, you will go to the job submission settings. So this job submission setting will help you to file the job from GUI to the remote machine. You can also file the job from GUI to the local machine. And once you do the simulation, you will get some output that you can visualize from visualizer in the 1D view, 2D view, and 3D view. And here you can see it also comes with the Python scripting engine that will help you to write your script in the editor. It also comes with the various insightful analysis that you can do, like the band structure, density of state, phonon band structure, electron density. So all these things you can easily do by the nano-device. Now, if we talk about the simulation engine that we have in the QuantumATK, so we have the DFT plane method for the recombination of atomic orbital for the materials, and for the devices level, it will combine with the non-constraint function method and also the sparse build function method. Similarly, for the material simulation, we have the semi-empirical, and for the devices level, it will combine with the non-constraint function method and the sparse build function method. And here you can see we have the classical force field and machine and force field simulation for the large scale simulation, and you can also go with the ticket and splice level simulation. So here you can see we have defined the number of atoms, and here we have defined the unit length of the structure. So suppose you created a structure that contains 100 atoms, then you can go with the DFT plane method. If you increase the number of atoms, like 10 to the power 7 atoms, then you can go with the classical force field and machine and force field simulation. So in the density function theory, we support two types of basis set, like the plane wave basis set and linear combination of atomic orbital basis set. So in this slide, I have compared both the basis set. So if we talk about the plane wave basis set, so it is designed for the periodic system, and it is conceptually simple, and it allows systematic convergence, and it requires main function per atom to achieve a good accuracy, because it will also consider the vacuum as a matter. Now here, if we talk about the LCO basis set, so it is designed for the non-periodic boundary condition, and it is very efficient. So in the LCO basis set, there is a large aggregation of CPU taps and memory as compared to the plane wave basis set, because it will neglect the vacuum of the unit cell. So in QuantumATK software for the density function theory simulation, we support the various sections correlation function like LDA, GPA, meta GPA, and hybrid is one of them. So here you can see we have taken the simulation time, and here we have the system size. So if you are going to simulate your materials and devices by using the DFT plane with the hybrid function method, you can see the graph will exponentially increase. So at a fixed system size, it will require more time for the simulation method. But once you are simulating your materials and devices with the DFT LCO with the hybrid function method, you can see the graph will increase linearly. So with the system size. Here you can see this is the pictorial representation of both the basis set. So if you are dealing with the hybrid function with the LCO method, then you will get the result within an hour or something. But once you are dealing with your simulation with the hybrid function method with the plane wave, then it will require a day or more than 1 day for the simulation result. So the conclusion is that the hybrid function DFT LCO is up to 10x faster than the DFT plane wave method. Now, if we talk about the devices level simulation, so for the devices, we have the density function theory that will combine with the non-constraint function method of simulating the realistic interface and the surface structure. So this DFT plus NEJF method is an accurate tool to study the interface and the electronic devices. So here you can see we have shown a two-flow device structure, where we have the left electrode, right electrode, and the center electrode. So this density function theory will apply at the left terminal and the right terminal, and density function theory plus non-equivalent function method will apply in the center region, so that you can calculate the transport property of the devices. So not only the two-flow devices and three-flow devices you can easily simulate, and you can also define their rising voltage, gate voltage, so that you can simulate their resistance, capacitance, and their IV characteristics. Now, if we talk about the bigger application, where you can use this QuantumATK software, so it cover a wide range of applications like semiconductor, batteries, solar and fuel cells, polymers, catalysis, even metal ceramic glasses. Now, if we talk about the semiconductor application, so you can simulate the property of new material, interface structure, contact and stacks, and their impact on the logic memory devices. Now, if we talk about the battery application, so you can design the novel battery materials for the cathode, anode, solid and electrolyte materials, additive materials, that is basically for the denser and the safer batteries or for the automotive and other industrial applications. Now, if we talk about the solar and fuel cell application, so you can model the known photovoltaic materials and devices with the improved photocurrent and the open circuit voltage. So for any kind of photovoltaic property, we have to follow the solar cell spectrum AM1.5 in the center region, and then we are going to calculate their photovoltaic properties. Now, if we talk about the polymer simulation, so you can design the polymer with the improved thermomechanical, thermoconductivity, and optical properties such as photoresistance, transparent polymers, and the polymers that is used for the tire and insulation industries. Now, if we talk about the catalysis, so you can predict and then use screening material for the improved catalytic activity of for the transition metal oxide, surface, and zeolite materials for simulating the property of truly semi-infinite materials. Now, if we talk about the metal, ceramic, and glasses, so you can design the glasses with the optimized optical and mechanical properties, thermal transport at the crystal and glass interface, and you can also simulate the property of predict the property of electronics, mechanical, and other properties of the metal below. Now, if we talk about the simulation procedure that we are going to follow for simulating any kind of structure in the quantum scale. So first, we have to create our structure by using the building tools, and once the structure is ready, you can go to the setups. So in this setup, we have to select the calculator first, and then analysis part. And once the workflow is ready, you can go to the job submission settings. And once you done the simulation, you will get some output, and that you can visualize from our visualizer in the 1D view, 2D view, and 3D view. So this is a typical workflow that we have to follow for simulating the materials and devices. So this QuantumATK also comes with the machine and force field simulation. So the question arises, why do we need this machine and force field simulation? So this machine and force field simulation is an accurate dynamical modeling tools for the complex structure generation, mechanical properties, thermal properties, electron phonon scattering, diffusion, process simulation. But other dynamical tools that is typically limited to 100 atoms, so because they require around limitation times, and also the quality of figure. But most of the industry will find any plus atoms to be simulated at a single time, and that is not practical with the quantum disk method because of the limitation times and also the quality of figure. So we will use this machine and force field simulation for the generation of the interdynamic potential, and that interdynamic potential we can utilize in the DFT and the classical force field. So for the atomistic modelings, we typically work within the three types of models that will provide a different level of accuracy at the different computational cost. So at the y-axis we have the computational cost, and at the x-axis we have the accuracy. So at the bottom level you can see we have the traditional force field, which is very efficient but often lacking quality of result. So in the middle one we have the semi-empirical models like the time bonding energy. So it can achieve a higher accuracy at the higher computational cost. So at the top we have the ab initio method like the density function theory. This can provide the higher accuracy but at increased turnaround limitation times. And here we have the machine and force field simulation that will allow to train a potential to reproduce ab initio result at the low computational cost, which is similar to the classical force field. So here you can see we have simulated a Markov Sacchini structure, and in this structure we have total 96 atoms, and we have performed 50 molecular dynamic steps at 16 core. So at 16 core, by using the density function and molecular dynamics, you can see it has taken 3 hours 21 minutes and 27 seconds. And by this MTP, that is a part of machine learning technique, and it is called moment tensor potential. So it has taken 10 seconds, and by the classical force field, it has taken 9 seconds. So this machine and force field will provide the accuracy as compared to the density function theory with the low computational cost, which is similar to the classical force field. So these are the list of force field application where you can utilize the moment tensor potential for the structure of the complex crystal, amorphous materials, structure of the multiple layer stacks like high chemical gates, the MRAM devices, crystallization and amorphization, formation of the defect cluster, defect diffusion, interdiffusion, thermal transport properties, and even surface processing by the atomic layer deposition and etching layer deposition. So this QuantumATK comes with the virtual nanorack, and this is the graphical user interface of this QuantumATK software, and it also comes with the Python programming interface that will enable the experienced user to efficiently implement the complex workflow, and you can also perform the advanced data analysis. So this is the GUI of this QuantumATK software that we will cover in the demonstration. And here you can see we have the various plugin toolbars, like we have the data filter, we have the builder settings, we have the workflow or settings, we have the job submission settings, we have the editor, we have the viewer, we have the custom script, and we have the database of the material as well. So here you can see these are the list of some advanced analysis and that is also possible by the QuantumATK software. So we also support the molecular dynamics simulation by the different method like the MBT, MPT, stress strain language, and even the optimization of the materials and devices that is also possible. You can also go with the dynamical methods for simulating the dynamic tensor and the optical properties. You can also calculate the Hamiltonian derivatives, transfer effect, adaptive kinetic Monte Carlo simulation, even polymer simulation that is also possible. So these are the list of some computable characteristics for the materials and devices that you can easily simulate with the different methods. Like we have the body structure, half-of the state, boron effective charge, chemical potential, effective mass, existence, correlation, potential, density of the state, charge density of the state, and even electrical property of the devices like IV characteristic, transmission spectrum, density, device density of the state, projected device density of the state. So all these things you can easily simulate by the QuantumATK. Now, if we talk about the job manager, so job manager is basically responsible for running the job from the to the local machine. You can also start the job from the to the remote machine. So in the local machine, we support the various submission mode like serial, threaded, and parallel simulation for the faster. And in the remote submission mode, we support the PBL, Scrum, SG, LSF, and also the direct execution. Now, these are the list of university that are using this QuantumATK software. So many more university, even Central University, Higher University are using this QuantumATK. So thank you for listening to this presentation. Now I would like to switch on the demonstration part. And in the demonstration part, I will show you briefly 2D materials, MOS tools, WSE2, and then what are the procedures that is required for simulating the materials and devices. So in the meantime, if anyone has any query, they can let me know. I will try to help you. I can see this is my software. So I have already opened. Yeah.
So Deepakji.
So this is the GUI of this QuantumATK software.
Deepakji, can you hear me? Hello?
Yes, sir.
Yeah, so your presentation part is over. Right?
Yes, sir, please.
So demonstration,
yes, sir.
basically you will first tell demonstration software process from your end, then let them start, or you will move step by step. What's your plan now?
Yes, right. So firstly, I will give some basic idea that is required for simulating the materials and devices, and then we will go with the hands-on.
Okay. So now you will take session from your end. So you give them details, no, right?
Yes, right.
Okay.
Yeah, I will take 10 to 15 minutes.
It's fine. You should have time. That's why I was asking. Yeah, please continue. Yeah.
Oh, okay, sir. That's okay. Okay, thank you. So this is the GUI of this QuantumATK software that is called virtual environment, and in the virtual environment here you can see we are under the project section. So in the project you can see I have created 2 projects, and if you want to open your existing project, then you have to click double click. I can see this project has been opened. Similarly, we can also create a new project by selecting this add option, and here we need to define the new file and then the directory, and then we have to select the choose option so that we can easily create a new project as well. I can see this is my example project that I am going to open. Now you can see this is the data filter, and here you can see we have the data filter, like everything is only data, no script. And these are the projects that I have already simulated. So suppose you want to filter out the data, so you can go with the data filter and you can select with the everything. Then it will show everything like creator structure and also this simulated data. If you want to show only simulated data, so just you can select the second one. Now you can see these are the data that I have already simulated. You can also select your own data filter by selecting this add new filter. So here you can see this is the builder session, and this builder session will help you to create a structure from this stress. So this area is called stress. So whatever this structure you will create, that will store here. Here we can visualize this 3D view, and this is the advanced panel toolbar. So this advanced panel toolbar will help you to create a design structure. Here you can see it comes with the various builders. Like you can see, we have the FM cantilever structure markers, pre-builder, alloy structure, icosahedron, interface builder, nanoparticle nanowires, elastic bands. So it comes with the various building tools for creating the structure, and even it comes with the build tool option as well, so that you can show the information about the systems. You can fit any unit cell, you can work any two unit cell, you can even repeat your structure as well. And even the stretching of the cell, that is also possible. You can create super cells. So all these things you can do by using the bulk tool, and here you can see it also comes with the device tool. So once you create a bulk configuration, then you can easily convert the structure into a device. So this is the advanced panel toolbar, and here you can see we have the workflow builder. And so first you have to create a structure by using the building tools, and once your structure is ready, you can take the structure into the workflow. And in the workflow here we have to select the calculator. Here you can see we have the different kind of calculator settings. The LC calculator, device SU, plane wave, or semi-empirical calculator, device semi-empirical, force field, machinal force field. When it comes to the ground state calculator, that will combine with the many-body potential. So once you select your calculator here, then you have to go to the analysis part, and you can see these are the list of analysis that you can do for any kind of structure and device as well. So this is part of the analysis, and here you can see it also comes with the optimization and dynamics. So if you want to optimize or you want to include some molecular dynamics, then you can use this optimization and dynamics as well. And here you can see we have the different kind of studies as well. And this is the moment tensor potential. So if you want to generate a new atom potential for a new material, then you can go with the machinal force field. Now you can see this is the job solution setting. So this is my local machine. I can easily fire any job from this GUI to this GUI only, and we can also fire a job from this GUI to any other machine. So here you can see we have the remote machine option, like you can see local machine, LSF, PBS flow. This is the SD, and this is the slow machine. So this is for the remote connection, and here you can see this is the editor. So you can export in writing the script. So here you can write your own scripting, and then you can go for the simulation. Even you can also save this file in the form of QATK, QuantumATK, Python file, HTML, and also the text file. You can see this is the viewer, and this viewer will help you to visualize the structure in this 3D, and this is the database of the material. So this is the online database. Now if you want to start from this page, you need to select this add option, and in the add option you can see we have the different option, like you can see this is the new configuration. So once you select a new configuration, then a default hydrogen element will be selected. So this is the hydrogen which is fractional coordinate point 000. Now if you want to change this hydrogen with any other element, so first we have to select, and here you can see this is the menu bar, the tool, this is the toolbar. So in the toolbar we have the periodic table, and this periodic table will help you to select your desired element, so that you can easily replace any element from any unit cell. Now if you want to convert this structure as a molecule, so here you can see we have the pentagon sign, and this pentagon sign will help you to create molecules. Here you can see we have the panel, and here you can see we have the different kind of elements. You can also choose from the periodic table, and it also comes with the various fragmentation, like the hydrocarbon complex, simple ring. So various kind of a molecule it comes here, you can see. And even you can also create your molecules by selecting the element. You can see this is the carbon, and here you can see these are the different kind of hybridization, like the unknown, mono, sp, sp2, sp3, fc weight center, and also the phase center. Suppose I would like to select this sp2. Now you can see this is the sp2 configuration of the carbon element, and I would like to select here. Now you can see we have replaced the hydrogen with the sp2 configuration of the carbon element. Now you can see I am going to create a benzene ring. I can see the benzene ring has been created. So this is the C6H6 benzene molecule. So this way we can create our desired molecules from this pentagon sign, and once the structure is ready, you can again select this pentagon sign. Now you can see we have replaced this hydrogen with the benzene molecule. So this way we can easily create any kind of a molecular structure. Here you can see we have the from file. So these are the supported file formats that you can easily import in the QuantumATK, like the Python file, HTML file, .xyz file, car file, CIF file. Even quantum is also .in file and postcard there, like postcard file and postcard file. You can easily import in QuantumATK, and then you can study their various properties by using the various So this is for importing the file, and here you can see this is the local database and this is the online database. So in the local database, we have the different options. We have the molecules, we have the crystals, we have the fluorescence materials and zeolite materials. We have the monomers, we have the gum state, elemental crystal, we have the 2D material as well. So this is the monomer for polymer simulation, and we have the 2D material as well. So we can also search our materials here. You can see this is the MOS2. And here you can see this is the property of this structure. So this is the conventional unit cell, and this is the hexagonal. Here you can see we have the lattice parameter, their ABC value. This is the symmetry information, and here you can see this is the DY number from where they have taken this material. Now, if you want to import this material into the builder, so you have to select this add option. Now you can see the material has been added in this steps, and this is the 3D view. So this way we can easily import any material from the local database. And suppose the material that you want to work is not available in the local database, then we can go with the online database. And in the online database, here you can see we have the crystallography open source database, and we have the material project. Here you can see we have the search protocol. I would like to select this best so that it will select every combination. Now here you can see we have the periodic table. So whatever the material you want to import in the builder section, so first you have to select their element. Here you can see I have selected this hydrogen and then oxygen. So you can see two elements have been selected. Now I would like to click on this search, then it will search every possible combination of hydrogen and oxygen from this crystallography open source database. Sometimes you will face this issue because we are integrating this QuantumATK with the open source crystallography open source database. So this is the reason we are facing this issue. Now if I select the REST SQL, and even if you know the COD identifier number, then you can easily enter in the builder section. Now you can see this site is down. So we can also move to the material project. So let me select the hydrogen and oxygen here and click on the search. And we are searching the material from the material project. Now you can see it is searching and it has found 19 structure. So you can see this is the combination of hydrogen and oxygen with the different crystal type. You can see this is the orthorhombic structure. Here you can see. We can also visualize our structure here, and this is the information about the structure. So this is the monoclinic. We can also go with the tetragonal, trigonal, and this is the S2 orthorhombic structure. Suppose we want to import this structure into the builder, so we have the various options. Here you can see it comes with the download option. So we can download this file and go to the builder, and we have to select this from file option, and then we can easily import the material. Now here you can see we have the arrow. Just you can select this builder, then it will take your material into the builder system. So this is the material that we have imported from the online database, and we have various options as well. So let me go to the online database. If I select this one, okay. If I select MONS, yeah, you can see it has found 13 structure, and here you can see this is the hexagonal structure of the MOS2. Now here you can see it comes with the various COD identifier numbers. So just you can copy this number and go to the builder, and here you can see we have the plugin toolbars. So for importing the crystal, we have the crystallography open source database, and for importing the molecules with the PubChem database. So we have copied this COD identifier number that we are going to paste here and click on this download. I can see the material has been downloaded, and even we have one more option as well. It also comes with the various no, here we don't have any tabs. Yeah, so you can see we have imported this material from the online database. Now if I explore this advanced panel toolbar, now you can see we have the FM cantilever structure. So if you want to design any kind of cantilever structure, so we have to drop your material here in the material section, and then we have to define the wedge size, the height, and the taper height, and then we have to define the clipping meter. So if I take any material from my steps, so let me import material from the local database. So in the local database, here you can see I would like to select this crystal, and here I would like to select silicon alpha. Now you can see this is the silicon alpha, and here we have the information about the materials. Now if I import here, I can see it will create a silicon based FM cantilever TP structure. Now we can also define the orientation as well, and once you define all the parameters, you can select this build option. Now you can see it has generated a silicon based FM cantilever TP structure. So by using this UI, you can create a structure within a quick time, and here you can see we have the amorphous rebuilder. So for creating any kind of amorphous structure, we have to define the sum formula, the density, and the jitter factor. So this jitter factor is directly proportional to the discontinuity of the system. So here you can see we can also change the sum formula, and once you define the sum formula, you can select this build option. Now you can see it has created SiO2 based amorphous material. You can also change the formula as well. If I take the ammonia-2 and this sum formula 200, and then click on this results. Now you can see. So this way we can easily create any kind of amorphous materials, and here you can see we have the Hessler data structure, and here you can see we have the different kind of structure type, like the combination of X, Y, and Z. So where X and Y is transition element, and Z is the main group element that we can select from the periodic table. So we can replace any element as per our need, and once you define all these things, you can select this preview. Now you can see this is the alloy structure, and then click on this create option, so that you can easily create a Hessler alloy structure. This is the icohedron, and here you can see if I show you the interface builder. So this interface builder will help you to create the interface between two materials. And if you want to create the interface between more than two materials, then you can use this interface, this one. I can see, let me import this silicon material at the site A. Now I would like to import another material from the database, and this time I would like to import gold material. So we are going to create an interface of the metal and the semiconductor. I can see this is the metal material. Now it is gathering the metals between the silicon and the gold materials. We can also increase the interface for this first side and second side, and we can also go with surface and cell settings. So it is creating the interface. Yeah. So you can see this is the interface between the gold and the silicon material, and this is the simpler structure that we get. Now if you want to change anything for the complex materials, complex interface, so you can go to the surface and cell settings, and once you select the surface and cell settings, so you will get the graph over the number of atoms versus mean, absolute, straight. So at this point you can see we have total number of atoms 15. This is the area, the rotation between the surface, and this is the strain value. Now here you can see we have the staining method, like the strain second surface, first surface, and most surface that we can choose. And if I select this point, now you can see the number of atoms has been increased, and I would like to select this apply. Now you can see we have created a complex interface of this gold and the silicon material. So this way we can create any kind of interface structure. And if you want to optimize, so you can just enable the algorithmic optimization settings, select the preview, and go to the create option. So after the optimization, it will generate a structure and the builder. So this is the interface builder, and here you can see we have the nanoparticle structure. Similarly, for nanoparticle structure, we have to drop the material in the core and cell, and then we have to define the core radius and the gap between the core and cell, and the cell thickness. So if I take this gold material in the core and the silicon material in the cell, and I would like to select this create option. Now you can see this is the nanoparticle where we have the core as a gold material and the cell as a silicon material. Now here you can see we have the nanowires builder. So for creating a nanowire structure, our structure should be a one configuration, like a simple PV face centered, and also the body centered PV structure. So if I select this gold material, now you can see this nanowire builder has been enabled, And here you can see we have the y direction, and also we can define the nanowire parameters like the radius and the surface energy. So this is the y direction 100, and if I show you the structure, you can see. So this is the word nanowire in the direction of 100. If I select this 110, I can see this is the 110 and this is 111. So this way we can easily create any kind of nanowire. Now you can see this nanowire is quite thin. So if you want to increase the length, then you have to use this bulk tool option. So in the bulk tool, you can see we have the repeat option, and this repeat will help you to repeat or structure in any direction, either direction A, direction B, and direction C. So here you can see if I take 10 times in the C direction and then apply, now you can see. So the length of this nanowire, gold nanowire has been increased. Now let me show some more plugin toolbars that we have. Here you can see how we have the nanotube builder, and this nanotube builder will help you to create any kind of nanotube by defining the site A element and site B element. So once you define the site element, you can go to the bond distance, and then you can choose the inner tube, center tube, and outer tube for the multi-wall nanotube also. So you can see at the site A and site B we have the carbon element, and if I select the preview, so it will show you the carbon nanotube. Now you can see this is the inner tube. We can also manipulate the plot vector and then m value. We can also go with the center tube. You can see this is the inner, this is the center, and here we have the outer tube as well. So this is the multi-wall carbon nanotube. We can also replace the site element for creating any kind of nanotube. So if I select this silicon element that is site A, then it will generate a silicon carbide nanotube. Now you can see. So this way we can easily create any kind of nanotube. So let me select the carbon only. So this is the carbon nanotube, and now you can see the length of this nanotube is quite thin. So we can easily repeat the structure in any direction. I can see. So the length of this nanotube has been increased 10 times in the transport direction. So this is the bulk configuration. Here you can see we have the information about the structure. So this is the bulk configuration. We have the atoms, we have the selection, we have the lattice type, and we have the primitive cell vector. And here you can see this is the unit cell volume, and this is the density of the unit cell. Now we can easily convert this structure as a device by using the device tool. So here you can see we have the device from the surface from the bulk and from the bulk configuration to the device. Now you can see here we have the device builder, and in the device builder here you can see all has automatically rejected their minimum electrode length at the left side and the right side. But we can increase the electrode extension length. Here you can see, and this electrode extension length basically will help you to reduce the scattering between the electrode and the center region. And if you want to increase the buffer region in the left side and right side, here you can see we have the increase option, we have the decrease option. So this way we can easily create any kind of devices as well. Now here you can see how we have the nano ribbon builder. Similarly, we have to define the site element, the bond distance, and even you can also passivate the structure with the hydrogen elements. And then you can go with the geometry, and in the geometry you can see we have the various options. We can go with the plot vector and an m value. We can also show the zigzag and the RZ structure. Now you can see this is the aligned with the plot vector. And if I select the zigzag structure, now you can see this is the zigzag and this is the RZ structure. So this is the graphene nano ribbon. We can easily replace the element for creating any other nano ribbon. Here you can see we have nano sheet as well. Similarly, we have to define the site element, the bond distance, and then you can go with the geometry. So once you're done, you can select this preview and then select this field option. And here you can see we have imported the material from the local database, and we have also shown how we are going to import the material from the online database. And suppose the material that you want to work is not available neither in the local database nor in the online database, then you can go with the plugin toolbars, and here we have the crystal builder. So this crystal builder will help to create or structure from these pairs. So for creating any kind of crystal, we have to define the space group, the previous lattice, the ABC value, the alpha beta gamma value, and the element and the personal coordinate point. So once you define all these settings, then you can really create any kind of crystal structure. So here you can see we have the space group like the triclinic, monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, and the cubic structure. So in the cubic structure, we have the face center and the body center. So if I select the face center, you can see this is the face center cubic structure, and here we can manipulate the lattice parameter. So if I select 141, sorry 14 for the silicon element, now you can see this add option has been enabled. Now I would like to select this add option and then the fractional coordinate point. Here you can see this is a default hydrogen element, and here you can see this is the structure. We can also replace the hydrogen with any other element. So just you can double click, and here you can see we have the list of elements from the periodic table. If I select the gold, now you can see this is the gold crystal, and if I select any other element, now you can see this is the silicon material. So here you can define a number of elements, there is no limitation, and once you're done, you can go with the preview. In the preview, you can see we have the primitive cell for showing the structure and for building the structure. We can also go with the conventional for showing and for building. So once you're done, you can select this build option. So you can see we have created a structure from the scratch. Now this is part of the building tools. So once you have created a structure while using the building tools, we can take this structure into the workflow. Let me show. Now you can see we have taken this silicon material into the workflow settings, and here we are going to add the calculator and the analysis part. Now you can see this is the calculator that we have added. So this is the LCO calculator. So for the material simulation, we have the LCO calculator, plane wave calculator, and the semi-empirical calculator. And for the devices, we have the device LCO, device semi-empirical, and we also have the force field and machine and force field and the ground state calculator for the material level simulation. So we have added the calculator, the LCO calculator, and if you want to manipulate any parameter in the calculator settings, so here you can see this is the main parameters. Like you can also include the spin tronics application in your materials. So here you can see the spin, like unpolarized, polarized, non-collinear, and non-collinear with the spin orbital coupling. We can also define the excellence correlation function, like LDA, ZZA, meta-ZZA, hybrid function. You can also choose the custom so that you can define your own excellence correlation function. You can see this is the pseudo potential method. We have the non-conserving and the potential. You can also go with the pseudo potential, pseudo FSI, FGS. So all these things you can define, and here you can see we have the numerical accuracy, and here you can see we have the various occupation method. Like you can see Fermi direct, Gaussian simmering, match phasor, and also cold simmering method. Then you can define the temperature and the density cutoff energy, and go with the K-point sampling method. So once you're done, you can go to the LCO basis set, and in the LCO basis set, you can see we have selected a ZZA excellence correlation function. So for this ZZA excellence correlation function, here you can see this is the predefined functional set. If I select here LDA, you can see this is the functional set for the LDA, and similarly this is for the meta ZZA, and this is for the hybrid function. Now here you can see we have the numerical accuracy. You can define the density of this cutoff, and here you can see we have the iteration control. You can define the tolerance value. You can define the maximum iteration step for simulating these materials, and here you can see you can also define the damping factor. Then you can go with the Poisson solver. So if you want to define the boundary condition in your materials, then you can choose the Poisson solver. So in the Poisson solver, you can see we have the different method like the direct conjugate gradient, non-uniform, Greek conjugate gradient, multi-Greek, fast Fourier transform, and fast Fourier transform for the two-dimensional. Like you can see, we can manipulate periodic, discrete, volume, and boundary condition. Basically, this Poisson solver you can utilize in the device level simulation. Now here you can see these are the basic settings that we need to manipulate before simulation. And once your calculator is ready, you can go for the simulation. Like here you can see we can also search. And before analysis part, if you want to optimize your materials, so we can do the optimization as well. So you can say this is the optimized geometry for the materials. We have the optimized geometry for the null elastic band, and we have the optimized basin as well. So optimization has been added. And then let me add the analysis part. Like you can see this is the band structure, and then I would like to add density of this state. So you can see two analysis part has been added, and here we can define the file name and then go to the editor file. So this editor we have to generate the file, and that is kept it editable. So before simulation, if you want to manipulate any parameter, or if you want to add any more analysis part, then you can write the script, and once the script is ready, you can save and then go to the job submission settings. Now you can see this is the job submission settings, and this is my local machine. We can also file the job from our local machine to the remote machine as well. So first we have to set up the remote machine option. Here you can see we have the job function settings. So we have the serial that will run on a single core. We have the threaded, so it will run on a single core, but we can manipulate the number of threads. Here we have the multi-process parallel, where we can define the number of threads and number of processors as well. So once you define, you can select this here, and here you can see this here. Now you can see the current task is pending. So if you want to run the job, you just select this play button. Now you can see it is going to execute. So this is the procedure for simulating any kind of this structure in the QuantumATK. So for the hands-on training, participants are requested to open their QuantumATK GUI. So just you can double click on this GUI. Yes, sir.
Yeah.
Yes, sir. We can start the hands-on training.
Give me 2 minutes. Install the system.
Okay, sir. So,
Are you discussing about installation also, or should I send them install?
no, I think yesterday I will install in some of the computers, and I have already told the process for installing the software.
Just please wait for 2 minutes. Just let them install.
Okay, sir. Okay.
And then you can start. So please wait. Hold on. So just
Okay, sir. You can just let me know when we can start. Okay.
Site ID in the file. Manas? What is the site ID? So we give it the file. What is the site ID? You install software. So help them. Site ID is. Tell them to those are installed, please help to your nearby student install. So have installed? Master put the site ID. Did you install? Rasa, did you install?
So here the site ID is
Site ID
is 39362. 39362. You can give your name as an administrator, and then you can give your contact details. Three nine three six two.
पीछे से ताकि पूरा पार्टिसिपेंट्स का व्यू स्क्रीन सीधा है आगे से पीछे से चले जब पार्टिसिपेंट लगे हुए हैं और सब अलग अलग एंगल से ताकि पार्टिसिपेंट काम करें give instruction very slow so that they should be able to follow you. Okay.
Yes, sir.
Yeah. Thank you. You can start.
Yeah. Okay. Also, for the hands-on training, how participants are requested to open their QuantumATK UI.
So all of you will open the QuantumATK. All of you open that, right? Yeah. So I think it's
Okay. So once you open this QuantumATK UI, you can go to the builder section for creating the structure.
all of you please open the builder. All of you have opened the builder session. So are you able to follow the screen? Okay. I have all of you have a mouse, otherwise with touchpad it will be difficult. If you don't have a mouse, you connect the mouse. Builder is where he has taken these many structures, but for you it might not be there.
In the left hand side, we have the builder settings.
You have opened the example projects?
Yes, example.
You open the example project, then you make it all the structures.
Yes, I have created actually a lot of structures, so this is it, and it is going in this test.
No,
So just you can select this builder. So once you open the builder settings, you will get some structure. Yeah. Now in the hands-on training, I am going to show how we are going to import the material from the local database like reference materials, and also I will show how we are going to simulate their band structure and density of the state. So for importing the graphene materials from the local database, first you have to select this builder, and then
Deepak,
you have to select
wait. Deepak, hello?
Yes.
Don't worry about what structure you have right side. Don't search for that. He is instructing you how to add some new material. Fine. So he told that go to open new material, you will add some material. So follow that. Forget about what's material there on the right side. Okay. So
yes.
Yeah.
Let me
Follow that. You just add new material.
So we will get these materials. ISIO2, SIO20, optimization, SIO2C materials. So don't worry about these stats materials. So these materials I have already created. So if there is no material, that is not our package. So no need to worry about these materials. Actually, these materials I have already created in my structure. So just to select a strong database, then you will find the zero interface. And in this interface, here you can see we have the molecule, we have the crystals, we have the fluorescence materials, we have the zeolite, we have the monomers or the polymers, we have the ground state elemental crystal, and we have the 2D material. Also for the importing the graphene material, we have to select the crystal. So once you select this crystal, here we can search graphene. So in the search box, just you can type the graphene and press the enter, then you will find the graphene material.
All of you want the graphene? Yes. All of you? Great.
So in the search box, just you can type this graphene, press the enter, then you will find the graphene structure and this is the hexagonal. And here In the right hand side, you can see this is the structure, graphene structure. Yes, sir.
Please repeat the unit cell and let us see the graphene, not the only two atoms in unit cell. Let's make it 3 plus 5 plus 5 so that we can see the how.
Yes, yes, sir. So once you selected this graphene from this local database, you just click on this add option to add this material into the builder. Here you can see this is the add option for adding this material into the builder section. So I hope everyone has been imported this graphene from the online local database.
For everybody who came to the builder, yeah.
Yeah. So once you have imported this graphene material, and you can see this is a simple materials with the two elements in the unit cell. Now, if you want to create a super cell like the 2x2, 3x3 some things, then here you can see we have the advanced panel toolbar. So in the advanced panel toolbar, you can select this bulk tool. In the bulk tool, we have this super cell. So here you can see we have selected a supercell in the bulk tool, and we are going to create a supercell of this graphene material in the direction of A, direction B, and direction C. Yeah, you can go to the bulk tool. In the bulk tool, you will find the supercell. Just you can select it, then you will find the supercell for creating hexagonal means complex materials.
What you have to repeat that? What that?
For making a supercell structure, this is the graphene that we have selected, and here we have to select this bulk tool. In the bulk tool, we have the supercell, and you can drag and drop to show all the information.
Understood, all of you? Yeah, there is no problem.
Now, we are going to repeat in the direction A and direction B. This is the direction A, this is the direction B.
People can please tell them how to repeat, they are not able to rotate that. So please tell them how are you rotating the structures.
By selecting the right click in the mouse, you can rotate the structure.
Right click press and rotate.
Yes. And if you want to reset a structure, then simply press Ctrl R. If you want to reset a structure, Ctrl R. Yeah. So here you can see we have the direction A, this is the direction B, and this is the direction C. So we are going to repeat in the direction A and direction B. So in the direction A, I would like to make it 2, and in the direction B, I would like to select 2. Just you can enter the value 2 times C in the A, 2 times C in the B, and then click on this transform.
Hello?
Yes, sir. So you can enter the value 2 times in the A, 2 times in the B, and then click on this transform. You can see we have created 2 by 2 graphene materials. We can also create 3 by 3, 5 by 5, 6 by 6 somethings. But at this time we are going to create 2 by 2 because once we create a larger structure, then the simulation time is going to increase. So during this session you can follow the same procedure that I explained, and after this session you can go with your own structure. So once you define the value 2 times in the A, 2 times in the B, then click on this transform. Now you can see we have transformed this simple structure into a supercell of the 2 by 2. We can relocate, we can relocate. Now, so once you follow these steps, and here you can see our structure is at the edge of the unit cell. I can see the structure is placed at the edge of the unit cell. So I hope everyone has been created a supercell structure of the 2 by 2. So can we move forward?
Yeah, please. Please move. Yeah.
Yeah. Now you can see how the structure is placed at the edge of the unit cell. We are going to make it centrally fit. So if you want to make it centrally fit, you can again here you can search the center that you find in the coordination tool. You can also search here center. Now you can see. We have the search bar. In the search bar, you can type center. Then you will find the center option. Here you can see we have the search filter. We are going to filter the center. And here you can see we find the center tool for creating this structure in the center A, center B, and center C. So we have to enable all these A, B, and C, and then apply. So just you can enable all these A, B, C, and then apply. Now again you can rotate and you can see our structure is centrally fit. If you want to reset a structure, then press Ctrl R. So I hope everyone has been created a centralized different supercell.
All of them created? Centralized? Yeah.
Now we are going for the simulation. So for simulating this centralized 2 by 2 between, you have to select this arrow, this bottom arrow, and then select this work provider. So for this simulation, we have to select this arrow and select this work provider. As you can see, we have taken this between supercell into the work provider. So this is our builder settings. In the builder, we have created the graphic supercell. Now we are going for the simulation. So for the simulation, we have to take this material into the work. So here we have the arrow. First you can select it and select this workflow builder. Now you can see we are under the workflow settings. Now you can see this is the finished structure that we have created. And here we have the QuantumATK. In the QuantumATK, you can see we have the calculator setting. Just you can click on this calculator. You can also find the calculator setting like that. You can see. So we have created a material and it is a graphene. So we have to select material calculator. So for the material, here you can see we have DLP calculator, plane wave, and the same calculator. So we are going to apply this CL0 calculator. So just you can double click, then this calculator will be added in the workflow. Just double click and you can see. You can also drag and drop in the calculator option. Like that. You can see the 20 digits. Just drag and drop. I can double click. Then the calculator will rotate below the graphene sector. Now here we are not going to change any parameter in the calculator settings, but every parameter you can change as per your research work. Now we are going for the optimization. So once you added this CL0 calculator, you can search here optimization. Here you can see graphene over here. This is the graphene supercell that we have created. Now if you want to simulate this material, so we have to take this material into the workflow. We can also drag and drop in the workflow like that. Here you can see. And we have one more option, just you can select this zero, select this workflow builder, and that's it. Anyway, you can follow. So our goal is to make these structure into the workflow settings.
This one is fine. This one is
Yeah, so we have added the graphene material in the workflow builder, and here you can see in the right hand side you can see calculator settings. Now just you can double click on the workflow calculator. And you can see the calculator has been placed below the graphene structure. Now if you want to manipulate any parameter in the calculator, so just you have to double click. So for manipulating any parameter in the calculator setting, we have to double click on the calculator settings and here. So you can go with the required parameter in this system. So after adding this CL2 calculator, now we are going to optimize our structure so that we will get a stable content. That's not the graphene superset. So here you can search optimization. You can search optimize, then you will get optimized geometry. You can also search OPT, then you will also find the optimized geometry. So in the search box, you can type OPT, and here you can see we have the optimized geometry. Now you can again double click on the type optimized geometry to pair these into the workflow settings. Then double click, and that's it. The optimized geometry has been added below the calculator settings. So once you added this optimized geometry, here you can search band structure. So after the optimized geometry, we are going to add the band structure. Then drag and drop element double click. Then the analysis part will be added in the workflow settings. Similarly, we can also add the density of the sphere. So for the density of the sphere, here we are going to search density. As you can see, this is the density, and here we have the density of the sphere. As you can see, we have added the density of the sphere in the workflow settings. So we have created this Latin supercell by using the building tools, and we have taken this Latin into the workflow builder, and first we have added the calculator settings, and then we have added the optimized geometry for the stable configuration, and once we will get the stable configuration, so based on the stable configuration, we are going to calculate the band structure and density of the sphere. So this is our complete workflow settings for the Latin superset. So I hope everyone has created a simple workflow for this Latin superset.
All of you are fine on the page? Yeah, good. On the page.
Okay. So once you created the workflow, here you can see the file name. So we can also change the file name of the project. And here we have the option to go to the job at history for this simulation. So you can select this arrow, and here you need to select this job at history. Then this interface will pop up. So here you can see this is the file name. No need to change anything. Just select this OK. Here you can see this is our example directory, and then we are going to save this graphic file. So this is a Python file. Select the save. And this is the job submission settings. Now in the parallel option you can see we have the serial, threaded and multi-process parallel for the cost simulation. In my system I have 12 cores, so I can go maximum 12 at the number of processor. And here we can also define the number of threads. 1 and then select this cell. So you need to select this multi-process failure, and here you can select the automatic number of failures, and in the process you can just cancel. But we can also define a number of processes. So once you define, you need to select this add. And once you added your project, in the left hand side you can see how we have the gathering. And in the task you can see it is pending. Now we are going to simulate. So for simulation we have to select this run option. So you can see we have the play button to start the simulation. Here we have the play button for starting the simulation. So just you can single click, and here you can see this job is going to execute. So in the right hand side you can see how this is our log file. So this log file will show you how the simulation procedure. I can see my simulation has been completed. So once your job is finished, you can go to the data option.
Overview job has been used.
So this simulation will take some time because it depends on the system to system. So in my case, I can define 1 core, and at 1 core I have 6 threads. So it has finished within a 35 seconds. Now, once this simulation completed, just you can let me know. So once this simulation completed, you just click on this data. So you can see this is the name of my project. This is a graphic underscore code result. So you have to select this data, and you can see this is my project. So here you can see it has generated three files. So this is the Python file, and this Python file is the input file for this QuantumATK, and this .hdf file is the output file that will store the information about the structure and the output file. And this log file will show you this simulation procedure. So this Python is the input, this HDF file is the output, and this log will show you the information about the background simulation. So for the output, we have to select .hdf file. So here you can go to the job solution settings, and this is my project name. You can go to the data, you can search the project name and select this HDF file. Then you will get the output.
Okay, what HDF file?
Yeah. So under the HDF file, you can see how we have the band structure, we have the density of the state, we have the optimized geometry structure, and this is the optimized trajectory. So this is our input one computation that we have created, and this is the optimized structure. So this structure is stable as compared to the one computation. So this one is more accurate. Now we are going to plot this band structure. So this is the band structure. This is the density of the state, and this is the optimized trajectory. So for the visualization of the data, any data as a band structure, density of the state, optimized trajectory, you just double click. Yes, please. So you can see this is my PDF file. And in the HDF, we have the different output file. We have the band structure, we have the density of the state, we have the optimized trajectory. So for plotting any data, we have to double click. I can see this is the band structure. If I double click, I can see it is going to plot the band structure data. Now if you want to plot any data, just to double click and you can see. You can also maximize it. So this is the band structure output file of this graphic supercell. Now here you can see we get the energy range from minus 20 to 28.1. We have the Fermi energy, and from 0 to 10 it is our conduction band, and from 0 to minus 20 it is our valence band. At the right hand side you can see this is the direct band gap value 4.05 electron volt. This is the indirect band gap value 4.04 electron volt. And this is the top of the valence band minus 2.33 electron volt. And this is the bottom of the conduction band 1.71 electron volt. So I hope everyone having plotted this value stacker up to.
What the value structure? I don't see what is the right or wrong now because the structure is not different.
We have simulated with predefined input parameter. So once you define the Now we want to export this value structure output. Here you can see this is the arrow for exporting the data. You can select this arrow, and here you can see we have the export format, we have the image, we have the PDF, we have the text format. So as per your need, you can select the format and you can go for the export option. So you can see this is the text format. Here I would have to export the data like the desktop, and this is the format. So the value structure output data has been exported at the desktop. That is why here you can see. You can see I have exported the data in the text format. Similarly, we can go for the density of the state. So just we can select the density of the state and then double click. So at the x-axis you can see we have the energy range from minus 20 to 28 volt, and this is the density of the state. We can also go with the projected density of the state. So in the projected density of the state, we can select the same orbitals and also the spin up, the spin down. So this is the density of the state output file. Now you can see we have the optimized trajectory. So just you can double click. Then it will show you the graph of the energy, force and distance with the time step. So this is the optimized trajectory of this graphene 2x2 supercell. Here you can see we have the play button that will show how the structure is going to optimize. So there are some little optimization in this structure. So this is the procedure for simulating any kind of structure in this quantum software. So we can follow the same process by learning our structure. We can import the data from this local database. Similarly, we can go for the data on a global like that. We can also import the materials like MS2, WSC2. So any different kind of material we can import. And once you import the data, you can do some modification by the Baliku, you can feed the same, you can make it centrality, you can create a superset, you can feed the stacker, and once you do some modification, you can take the stacker into the workflow settings. So in the workflow settings, we have to select the calculator and the analysis bar. So once your workflow is ready, you can go to the top solution settings. And once your simulation is completed, then you can go to the data, select your project file and go to the SQL file. Then you will get the output.
Question?
Yeah, if anyone has any question, they can unmute yourself and yeah.
So here we can directly see the graph of the trajectory graph. Okay.
Yes, right.
Suppose we want to see the data. So very data. Suppose we have to plot that data in Aussie. Then how we can get that particular data? So directly we get
support the experimental.
Just plot particular graph. Suppose it's energy points. We need the energy points. Then how we can get that?
Yeah, so just you can disable this force and this phase. You can see the energy point and get the time states.
So
Then we have the export. Yeah. Yeah, we can go to the export and we can go to the text format and go to the export and text. You can select your file name, select the location and click on receive. Then it will export the file, text file, and that you can further use in the origin.
Then in origin we can see that particular data.
Yes, yes. But like this is the benefit of the QuantumATK. Here there is no need to take the data from India. So just it performs to be like that, uploading the data, visualizing in 1 DB, 2 DB, 3 DB.
Any other question? Anyone else? Any question?
But here more is option.
Sir, I'm Nivin.
Yes.
Yellow Fruit Creek student. Sir,
Yes,
if
yes.
I had done IDFT in another software like WASP or something, and can I be able to transfer those files here, import those in this QuantumATK for some delay simulation or something?
Yes, right. Here you can see we have the data section and here you can see we have the from files. If you are working on the mask, here you can see we have the mask, just you can select and you can select your output and input file. If you are working on the quantum expresso, just you can select the quantum expresso and then working file E4 in this QuantumATK software and then you can go for the further simulation or visualization. Yeah, and even here you can see we have the tool and in the tool you can see we have the custom picture. So in the custom picture you can see we provide the GY for the Zipa, Orca, Quantum Espresso and Vast. So their input file is easily created by the QuantumATK. You can see this is the Quantum Espresso input file that we are going to create. Here we can add the configuration, calculate the rating, I can see the mathematics. We can define all the settings, the basic settings, the control parameters, systems, electron, and access for the optimization. So once you define all the settings, we can easily convert it and find the ask.
Please repeat after tool. After tool.
So just to calculate the tool, here you can see we have the custom scripter. And in the custom scripter, you can select the scripter option. and the frequency bars and the space. So all this interface will need to be there. And this is my contact details. So for this system, if anyone plays any system, you can just click.
Deepak, you have few more questions?
Yes, please.
This tool can be used to simulate like the bulk device characteristics.
Yes, device selection is also possible. Here you can see we have the device tool. Here it is. This is the device tool. Suppose we have taken this, you can see this is the silicon material. If I convert this structure, I will work. If I go in for this configuration to like a not standard device structure, that we are not having the complex structure for creating a network. So first we have to create a supercell. So here you can see the supercell option. I'm going to repeat at the base center and see. So once we have created a base center, I am going to repeat our structure. Here you can see you can see we have created a complex structure. Now this is structure is ready for the device. So we are going for the device from the bulb, and here you can see. This is the electrode length of our left side, right side, and this is the electrode distance. Now you can see, if I show you this one, it is showing as a bulb configuration. And if I play this device, you can see. The device configuration. Even we can also define the routing as well. You can see this is the routing option. If I select our PN junction, PNP or PN junction, so we can see we select this select region. You can see this is the N type routing, P type routing, we can also find that concentration rate. If I select this center region as a P type routing, I can see the N type routing, P type routing, and here I am going to take PN type routing. We have created the Lentian lines. And for the output, like the IP things, we have to take this structure into the control. First, we have to have the calculator, device calculator, and then we can go for the IP. Okay, you can see this is IP calculation.
I have a question.
Yes, sir. Yes.
So I have a question. So if we take the lateral infrastructure up to two materials, like if I take two materials and then you want to similar like doing
Yes, that is also possible.
so
You can take two materials, three materials, only
actually in the simulation pattern we have shown here. So we have only two or three atoms and in the whole layer is up to I think that 2 micrometer by 2 micrometer area can I take and then I can put a lateral infrastructure of 2 micrometer by 2 micrometer area and our question is here we have a observed evolution so can I take
Yes, sir. Yes, that is also possible.
if you have a time I can show one simple PN junction
With the different electrode, right?
simple PN junction like lateral infrastructure.
Okay. So, any like the first we can measure the distance by the distance internet here. You can see that the distance measurement, intermeasurement, and the diameter intermeasurement. So we can say it is going to measure the distance in the system that we can consider like convert into the micrometer and so once we measure, yeah. is reduced as 90. We get is 135 minutes. Now we have to create a superset, a lateral referral structure for the referral structure. Here you can see we have the interface builder, interfaces, and also we have the interface builder. So can you let me know any example of the model that I want to create a referral structure?
So I'm asking for evolution interfaces, PN junction. One PN material and then.
Okay, I'm going to start the basic. Yeah, that is also possible. We have to import from the database. Then we can go with the WC2. So this is the double layer material. So we can go with single layer. We can take here. We can also create a layer by adding structure as well. Like I say, if I go to the surface and say, and select this one again, I can see. And this is the MS2, this is the WC2, and then we can go further for the devices as well. If you want to create the C direction, transport direction, so we will use the circuit superset, then we can send it. Here we have to take 12 minus 2. You can see we have created, and we can make, we can serve the axis. Yeah. Then we can make centrally PTR, please. Yes, please tell.
Sir, I have a random student. Sir, I have a question. Can we introduce defects in graphene?
Defect, right? Yeah, defect is also possible. Yeah, just a second. Now we can go for the replacement of the mat. Here we can replace the WC2. We can also take another layer of the WC2 and the top side, bottom side, any layer, and just we can introduce below. Now let me go to the defect in a graphene sheet. So this is a graphene, right? If I take as a superset, if I take 5 times CA, like this, we have created a graphene sheet, and if you want to introduce the detect over there, like a lot of procedures introducing the detect. We can do some manually detect like replacement of the particular element, or we can go with the workflow builder, let's say the defect option. You can see quantify defect generator, defect pair generator, generate defect computation. So you can go with the defect and get we have the general option, we can be specific. This is the defect parameter. We can go with the substitutional, vacancy, interstitial, split interstitial, and custom. We can go with the substitutional. Here we can place the element from the periodic table, and then we can go with the. We can also repeat our structure. Defect is also possible.
Hi, Deepak. So earlier, actually, I think you created lateral infrastructure earlier. I mean, lateral infrastructure, I mean, on a single substrate, suppose when there is silicon or silicon oxide, on the half of the area of the silicon substrate will be like impregnated, the other half portion will be like it is like a single layer only, but on a lateral side. But the picture whatever you showed, I think earlier you showed whatever you showed. So it is not like I want a two layers distance, two layers adjacent on a single block. That's why I asked.
Yes, sir, possible. That is possible. So we have to create our second layer as well, and then we can work. I suppose if I take as a if I test with the oxygen, yes, I will. So let me roll this substitution. Here I would have to select the oxygen 50% so that it will become insoluble. That's it. We have created a SIO, which is not the perfect one, but this way we can do. And we can take control C, we can go to here, we have to make some vacuum space. So for that, I will use the lattice parameter, and in the lattice parameter, in the A and B to this will be positive value, let me select 10, and then I would like to take 50, 20, plus 20, and then make it centrally fit. And then we can place the SIOs of state here. And so we can remove undesired items from the usage. And we can also replace some of the clipboard.
So this Deepak, I just want to know. So recently Synopsys adopted FDV, right? So we can also do right mass interaction on this type of structures.
Yes, that is also possible. So there we can do
Like how to convert FDV here? This is an option.
So at this QuantumATK, at this version, that is not possible because I have installed this 2025.06. They have introduced ESP1 version. So in that version, that is possible.
Any other question? Anyone else? No more question. Then let's thank the speaker. With a big round of applause.
So,
yeah. Fantastic session. I think you have given a real insight of the QuantumATK, and you just get a lot of benefit. So I think I suggest all of you just to do more practice by yourself, and there's a fantastic documentation on docs.quantumatk.com. I hope that link is working right.
yeah.
Huh?
Yes, you can go, yes. You can just go to the QuantumATK documentation.
So,
Just you can go QuantumATK and later the documentation, tutorial, publication papers, so on. You can
fantastic database. At least I have gone through whatever tool I saw the best database that QuantumATK maintains for the So you can explore this, you can find plenty of examples there. So you can explore more, do more practice for next week tomorrow, and it will give you more hands-on. So on this note, thank you once again, Deepak, for giving your time, and have a nice day. Thank you.
Yes, thank you so much. Thank you. Thank you everyone. Thank you.
So I hope all of you learned something. Everyone excited? Okay, so license will work. So do more practice, and if you want, and main thing is the doc.quantumATK.com. You mentioned a nice database. You can see the examples, whatever things you know, everything is written here with proper diagram, proper everything. You can follow that. You can learn more. Then, if you want more license or other thing, you can request or access for a student license to explore more, or further you can request your supervisor something. You can buy license if you want to work with this. Okay. So on this note only, we are closing today's session here only. So thank you for joining. So yeah, tomorrow 9:30 we will meet. But before that, All of you please come. I hope all of you coming to the dinner, right? You got an invitation even? Fine. I hope I'm not missed. I have sent you everybody. You can check that you have registered, then you must have got the email. Fine. So come for the Astronomy Club. Have you seen the Astronomy Club? Huh? All of you have seen that? Those who have not seen, you will call to us or one of them help you. Come there by 7:30 and some faculty will come from the electronics engineering department to interact with them, talk to them. If you have any kind of doubt, fine. Ask them and try to interact as much as possible. Okay? Fine. Okay. Thank you for your attention. Thank you.